Okay guys, this is section 3 of the radioactivity topic, and really it's kind of the main one. So we've done all our background, we know what radiation is. It's stuff that comes out in nuclei. We know there are certain types, we know there are certain properties. We know those other background factors when you're trying to take readings. Where else does radiation come from? How does it affect your readings? What else do we need to consider to stay safe? But we haven't actually answered the question, why are some elements radioactive? And more importantly, rather than GCSE version, at this level, why are some isotopes of every element radioactive and why are some not radioactive? So all the way from helium, the single proton element, all the way through the periodic table, we have families of particles that are nominally the same. They are all chemically the same. Some are more common than others. So for example, neon 20 is the most common version of neon. It is not the only one, but it does make up a huge percentage. I will just briefly look it up in my table and double check it. It makes up 90.92% of all the neon around, because the rest of them are all mad and unstable. So why are some particularly unstable and crazy and fall apart very, very quickly, very rapidly, very frequently, very high probability? And why are some not? And why is it not the smallest one? Surely the smaller ones would be more stable. No, it's all about those important fellas there that we mentioned in our last topic. In chapter 20, I should say this is chapter 21. Bing! So in chapter 21, when we go back to chapter 20, it was all about those unsung fellas, the neutrons. Okay, everything to do with the nucleus is about the neutrons within it. So my green neutrons in this picture, too many, too little, just right. A bit like Goldilocks and her porridge. So jump into the chapter, and we're going to go to section 3, and it's called modes of decay. So all the stuff above it is to do what we detect, and things to think about when you're looking at experiments to do with radioactivity. Counts, numbers. We're now shifting into a new phase, which is why are things radioactive. Okay, so the radiation tells us about the nucleus, because the more radiation comes out, the more unstable the nucleus. So what is it that's inside the nucleus that's causing things to change? And we've touched on some of it already, depending on the type of radiation that's given out, but there's many, many more. Okay, so lots of the key ones only happens at high energy, particle physics. We're looking at the main things. So, periodic table. When you look down at your old periodic table, at the beginning, things seem so simple. You just have single numbers on your isotopes, and at GCSE in particular, the other isotopes were basically twice as big. Well, that only works up to a point. And what we have here, very famous, and I'll break this down a bit more as we go into chapter 22, we have something called the value of stability. So some elements are more stable. These black dots on the periodic table, which is basically numbers of protons here against number of neutrons, we have basically some elements that are more stable than others. Sorry, more isotopes of elements that are more stable than others. So for example, there's a group here, just from that value of stability downwards, and another group there, where there's quite a few of the isotopes of that element that are quite stable. Okay, so there's quite a few that will remain and are commonly found around us in the world. So therefore, those are the ones that tend to worry about in chemistry. However, when we go further down, all of this, all the way to the edge here, are different isotopes. So again, towards the middle here, you've got a lot of isotopes that tend to give out a certain type of radiation, and isotopes that are bigger, more massive, more neutrons that are also radioactive and give out a different type of radiation. So it's all about trying to get down to the bottom of this valley. Imagine a valley, rocks always fall down. Where do you find the rocks? You find them in the bottom. Those that studied glaciation and all that kind of stuff, that's where you'll find your rocks. Lowest entropy level. So if you'll always find rocks down in the bottom, so you can use that analogy. There's also, it gets more complicated, we've got cliffs at one end of the valley that you can't see on this graph, but we'll come back to, and you have a slope down as well. So things tend to roll down towards the bottom. If you go to the large numbers of protons, you'll find that those elements are all radioactive. So at the bottom end, bottom right side of your periodic table, all of those elements are unstable. They will decay into more stable elements. Okay, but some elements will decay just into other versions of the same element. They'll decay into other isotopes. Most of them don't. Most of them will move down towards this end, and there is one area around about here that is incredibly stable. You can tell because the width of the valley is very narrow there. Okay, now crucially, that line up there is where your numbers of neutrons equals the numbers of protons. Okay, so be wary. At the beginning that's enough for stability, but that's, if you go back to what we were doing with the liquid drop model, they're the lumpy ones. Okay, once your atom starts to get round, the nucleus starts to get round, then you need extra neutrons. So if we follow this up, a general rule, go up from 80, 120. If you go up from 60, it's hitting around about 85, harder maths, etc. So you work it back, but basically you'll need about 1.5 neutrons to every proton to space them apart for the nuclear strong force to hold them together. So it's all to do with that force that binds your neutrons together, your nucleons together. Okay, so a little bit back on that, and a reminder from last chapter, it's going back to the repulsion, which is trying to tear your nucleus apart and having enough neutrons to do it. So if, and this has appeared before, if they were asked to sketch one, then you just need to make sure you go through, I would go for that idea, 1.5, use 80 and 120. Down at the bottom, not many of them, but you start to kind of get up to about 20 and it starts to come away from your 1 equals 1, proton equals 1 neutron line. Okay, and a little bit of a hint, which we'll work into why, well, we can work it out from the results, which of course is where this table comes, where this graph comes from in the first place. So, crucial bit to highlight. Just beware if you're looking on the internet for this. It's very common. They will have the number of protons because that's what controls the element itself. However, up the side could be the number of nucleons rather than number of neutrons. So the scale will be bigger. Okay, well, the scale will be smaller. It will go up to a higher number. Okay, so just be wary what's plotted on here. Should be neutrons against protons. That's what the version I'm going to use. Okay, crucially, it's really important because this graph, because it tells us what's going to happen to our particles. We can work out which isotope is going to decay how. Okay, and it's all to do with the idea of falling into the lowest energy level. Okay, so we'll look at that and we'll break it down. So let's zoom right into a small section of that graph. Here we go. So it doesn't matter what the number is, but let's not assume it's in the first 10, 20. What we get is a movement depending on the radiation that comes out. Okay, so to break it down into basics, let's just treat it one step at a time. If we were to take an alpha decay, please again notice neutron, so I'll highlight that there. If we were to have an alpha decay, then what you've got would be an alpha particle coming out of your parent nucleus. Okay, so this is your original unstable nucleus, often signified by an X, or they may give you something specific, and then you subtract 4 because you have lost 4 nucleons and 2 protons. So in terms of our model, here we go, here's our neutron, and it's not held it enough. There's your alpha particle come off, and it's come off with high energy, so it's shot off in that direction. This momentum conserved, energy conserved, so very fast. This is much more massive. This will move slowly because it has a low velocity, big mass, small velocity, small mass, big velocity. Okay, so that will shoot off into the direction. What you are left with is our daughter nucleus, our smaller nucleus. Okay, always less massive. That's crucial. Always more stable. So what we've basically got is that loss of the alpha particle, and it's worth breaking it up. So 2 protons and 2 neutrons. Okay, just to stick with this, I'm going to use capital. I try and avoid that really because it gets confusing. So 2 protons and 2 neutrons. So in terms of our graph, our proton number drops down to, our neutron number drops down to. So your daughter product will be here on the table compared to where it originally started here. Okay, so it doesn't matter where you're starting on the graph. Let's say somewhere up here, you are going to move along to and you're going to move down to. Okay, now if this is nucleon number, still protons are going to go down to, but you're going to change 4, so just be wary, but mostly in the exams we'll just get neutrons to make it easier. Okay, so what do we got? Well, the others are a bit more complicated. Beta minus, we have a neutron decay into proton, so we lose 1 neutron but we gain 1 proton. Okay, so that's your idea. We also have an anti-neutrino that comes out, but that's about conservation of energy. It's not where is our particle going, where is our numbers turning to. So this is just a plot of where you are going to go to. So this is like your map. So proton numbers again is going to increase by 1 because it's a -1 that comes out. So -1 subtract 1, +1 subtract 1 gives you that original number. So I always work backwards with these. If I know what comes out, it's easier to work out that. Likewise with alpha, I should say. So that means that a beta minus decay is going to be this one here. Okay, so beta minus, I don't know if that's very obvious on your diagrams. Beta plus is the opposite, so it goes off in the opposite direction. So it will move it up the neutron number, but down the proton number. Okay, so that's beta. Change there. Okay, I'll come back to this one in a second. So that beta plus is the decay of a proton, so you're going to lose 1 proton and you're going to gain 1 neutron. So go up 1 but go left 1. Now some electrons, and I mentioned this, and it is one of the examples on the Feynman diagrams in chapter 20, you can capture an electron. Now because of the nuclear weak force interacting on it, what you'll find is basically it does the reverse of what's happened in a beta decay, in that the electron goes into a proton, it's attracted by a proton, and because of that weak force it then changes the quark structure in the proton to become a neutron. That's long-winded, so again, let the work do it. So if you have Z and you add on a negative charge, a proton number of -1, I know it's not a proton but it's a negative charge, then it becomes Z -1, doesn't change the mass, the nucleon number, so therefore what you've got is you've not actually really lost anything. You've kind of lost 1 proton, okay, but of course it's still there. You've gained 1 neutron. So that's a different thing, but it works like the beta plus. Excuse me, that's not very clear as well. So that's a beta plus there. Okay, or electron capture. The end result is that you've got a nuclear change that increases its stability. Okay, so it doesn't actually matter on the process, different processes, but they still end up at the same place. One plot diagonally up and left. Nuclear emission, so again, we can get different things. So you can spit out various particles, you can spit out a proton, you can spit out a neutron. So fairly obviously, if you spit out a proton, you've lost a proton, you've lost a neutron. So you can get simply proton or neutron emission, and that happens quite a lot. Neutron emission is quite common when we induce that to happen. So when we induce effects in a nuclear power station, in a reactor, wherever the reactor is, then that can be different. We enrich the usually uranium, for example. So if you have enriched uranium, you've got extra neutrons, it's unstable. You might also have heard of enriched uranium because it's very dense metal. It's used in shell tips for armor piercing shells to fight tanks, and it's that high density tip that makes it through. But again, it may be good for piercing armor, but it also leaves radioactive shards everywhere, so you get contamination of a neutron rich source. So another side issue, another side fact. So these are a bit more rare, okay, where you have too many protons or too many neutrons to be stable. Yeah, so maybe you've got two neutrons for every proton. That's far too many neutrons. So you can either split that out, or if it's that kind of size, it's more usually to split alpha decay. Now if you're thinking, but that same number of protons and neutrons, it still makes it closer to the stability line. So big nuclei tend to always decay by alpha sources. Okay, so these are big nuclei. Okay, worth putting in. Can happen in others, but definitely in big nuclei. That is the main source of decay, alpha decay. Beta plus, beta minus, smaller particles, smaller nuclei, smaller radioisotopes, radioactive isotopes. So those radioisotopes will give out beta to fall down the side of the valley, whereas alpha is falling from the head of the valley, ones that are really big and falling downwards. And these are, say, a bit more rare. Now, if we go back to my stunning picture from the beginning, a bit may drop off this. Okay, so this one here, for example, this has too many neutrons. What you'll find is that the neutron will decay into a proton plus an electron, so an electron shoots out. There we go. Plus an antineutrino. Okay, because it's a lepton and an antilepton. Okay, oops, I won't underline both those, so don't forget that. But again, doesn't feature in the maths because it's almost no mass and it has no charge. So in this one, what you're doing is you're moving them from the side where you had too many neutrons. So again, on our sketch graph, there we go. This was our neutron side, this was our proton side. If you got too many neutrons, you're up here, that falls downwards, or rather, excuse me, it falls diagonally downwards into your valley. Okay, so neutron rich are these ones up here. Neutron poor, now again, that's actually the same vertical lines because it's the same isotope, same number of protons, but again, it's going to fall diagonally that way. Okay, so the motion is always towards that center stability line. If it was to take, let's get that out of the way, if it was to take something that is really massive, then again what you're doing is giving out alpha, so that's at 45 degree, that's down 2 and along 2, so much bigger arrow, much bigger fall, and again it's still working towards this this area that's most stable, that's around about this area. Okay, and everything generally will end up there. Again, we'll pick up on that in chapter 22. Again, it links in with astrophysics. So lots of links going on. However, as I was going to say, you've summed that out. You've got rid of a lump of energy equals mc squared. However, it's usually still a little bit unstable. It's called metastable. So some materials are actually quite good at holding on to their meta status. They're metastable, and so they are good sources of gamma rays. Technetium is one, often used in medical research, so technetium 99. Now what happens there, as I said, is where you've still got excited daughters. I'm sure we can make a joke out of that, but you know, there is energy left over, and so what it does is it de-excites, and it gives that, it falls down to its most stable version, ground state, notice terminology, by giving out photons. There's no structural change, so basically no particles. I was about to say nothing, but that's not quite true. No particles, just energy. Okay, so it's all about giving out that photon of energy equals HF. There we go. Okay, so how does that work? Well, let's just link that in. Exactly the same as energy levels for electrons, apart from a couple of bits. So here, for example, is magnesium 27. Okay, and what that does is that decays by a process to become aluminium 27. Okay, but that aluminium, as it's saying here, decays by beta minus, etc., and so on going on. So you don't have the what you'll have is the change in proton number, of course. So here is our beta decay. Could be an alpha decay, in which case it's a bigger drop. But again, we can think of the idea of energy levels of each isotope. So how much energy have they got above zero energy level, their ground state? So what they'll do is they'll give out some energy by firing out a particle, and they'll drop depending how much energy beta has. If it's alpha, it will fall a definite value because they all have the same value of energy. However, for beta, depending on the neutrinos that come out, you'll fall different distances. So you're left with this excited aluminium, so what it has to do is it fall back down here, so it'll then give out 1 or 2 or more, depending what energy level it lands on, photons of radiation. Okay, and that's your gamma rays that are coming out there. Okay, so depending on it, the gamma ray level is that many electron volts. Now again, a couple of things to notice. One, we're now talking mega electron volts. It was killer electron volts when we were doing electrons. So we have a lot more energy coming out of the nucleus than we do by de-exciting electrons. Second thing to notice is this, again, the diagram's not great, but it's best I can find. It's about the change in energy. So again, it doesn't matter too much. It's that change in energy, but again, 0 is up at the top, and these are actually negative, and the numbers should get bigger as you go down. So just be wary, this diagram's not great. Okay, this is the maximum negative energy. But the idea is the same, so it's all about trying to get lower and lower and lower and more stable. So crucially, the processes aren't hard, but what they're all about is they're trying to get rid of the right number of the right type of particle to end up in that more stable position. And the stable elements, the stable isotopes down here, tend to be the ones that are on the periodic table. I should say tend to be because, like the chlorine example, which is around about here, there are 2 stable versions, 25% of one, 75% of the other, so your average is on the table. So again, periodic table will be for each of these columns the average of the stable nuclei. Okay, but yeah, your periodic table is that center stability line. Okay, thanks guys.